All right, let's talk about an invisible force that completely shapes our weather. A force so powerful it's like having a car sitting on your desk. We're talking about air pressure. And by the time we're done here, you're going to understand exactly how we measure it and, even cooler, how you can use it to figure out what the weather's going to do next.
So, I want to start with a number. Just look at that. 11,000 pounds. What in the world could this massive weight possibly have to do with the air that's all around us right now? Any ideas?
Believe it or not, it's the air. That's right. The amount of air pressure pushing down on a totally normal school desk is the same as the weight of a 50-passenger school bus. And that fact, as wild as it sounds, is the key to understanding, well, everything, from wind to weather forecasting.
So here's our game plan. First, we'll get a handle on the air's hidden weight. Then, we're going to decode what atmospheric pressure really is. After that, we'll jump in a time machine to see the amazing invention of the first barometer, and then check out its modern liquid-free cousin. And finally, we'll tie it all together so you can see how this one force helps you predict tomorrow's weather.
Okay, first up, let's wrap our heads around this incredible idea. It sounds like a metaphor, but it's physically true. Every single one of us is living at the bottom of a giant ocean of air.
And this pressure is no joke. It's so intense that astronauts need those special pressurized suits to survive out in space. You know, without that suit pushing back, creating the same pressure we feel on Earth, their body fluids would literally boil. The atmosphere is our own personal, life-sustaining cocoon.
Okay, so this brings us right back to that school bus on the desk. It's the most logical question, right? If there's that much weight pushing down on us and on everything else, why aren't we all just completely flattened?
And here's the secret. Atmospheric pressure isn't just pushing down, it pushes on us from every single direction at once. Down, up, sideways, you name it. The force pushing down is perfectly balanced out by the forces pushing in from all the other sides. Think of it like this. If you put a 33-foot tall aquarium on top of a desk, yeah, it would be crushed. But if you sink that same desk inside the aquarium, it's totally fine, because the water pressure is pushing equally on all its surfaces. We're just perfectly adapted to live inside our ocean of air.
So we've got the whole weight of the air concept down. But what's actually causing that pressure? To understand that, we have to zoom way in, from the scale of oceans down to the scale of molecules.
Okay, so here's the technical definition. But what does that really mean? Well, unlike a solid or a liquid, the gas molecules in the air aren't stuck together. They're zipping around like crazy, constantly moving and bouncing off each other and off of every single surface they touch. That endless collective bombardment, that's what we feel as pressure.
Here's a fantastic way to picture it. Imagine billions of tiny little bouncy balls in a sealed room, just going wild, hitting the walls over and over again. The constant thumping of those balls creates an outward force, right? Well, the atmosphere is that room, and we're just living inside it, feeling that constant bombardment as pressure.
And of course, scientists have measured this force very precisely. At sea level, we call this standard pressure. Now, you might hear it talked about in different ways. Meteorologists love millibars, while U.S. weather reports often use inches of mercury, but they all describe the exact same force. And that last one, inches of mercury, that's a huge clue as to how we first figured out how to measure it. So how in the world did we first measure the weight of this invisible stuff? For that, we have to go all the way back to the 17th century, to a brilliant student of Galileo who finally cracked the code.
So back in 1643, this guy, Evangelista Torricelli, was the first to really describe the atmosphere as a vast ocean of air. But he didn't just stop there. He actually came up with an ingenious way to measure the pressure it creates. His invention, the mercury barometer, was so good it became the standard for centuries.
The process was just beautiful in its simplicity. Torricelli took a long glass tube, filled it to the brim with mercury, and then flipped it upside down into a bowl that also had mercury in it. Now, some of the mercury flowed out, but not all of it. A column stayed up in the tube, and it was held there by the air pressure pushing down on the mercury in the bowl. So the height of that column became a direct measurement of the air's weight. If the air pressure went up, it pushed the column higher. If it went down, the column fell. Genius!
But wait a minute. We all know mercury is pretty nasty stuff, right? So why was it the liquid of choice? Why not use something simple and safe, like, I don't know, water? Well, the answer comes down to one really important property: density.
See, mercury is over 13 times denser than water.
It's just incredibly heavy. And because it's so heavy, the atmosphere can only hold up a column of it that's about 30 inches high, a pretty manageable size for an instrument. If you tried to build a barometer using water, you'd need a tube nearly 34 feet tall. That's almost 3 stories high. Just totally impractical.
Torricelli's invention was a total game changer, but let's be honest, a big glass tube full of toxic mercury isn't exactly something you can stick in your backpack or on an airplane. So the need for something smaller and more practical led to the next big breakthrough.
Say hello to the aneroid barometer. The name literally means without liquid. Instead of a column of mercury, it's got a small, flexible metal box that's been sealed up with some of the air taken out. When the air pressure outside goes up, it squeezes the little box. When the pressure goes down, the box expands. And a clever little system of levers and springs makes those tiny movements show up on a dial that you can actually read.
So let's put them side by side. The mercury barometer is still the king when it comes to pure accuracy. It's what we use to calibrate other instruments. But the aneroid barometer totally won the battle for everyday use. It's tough, it's portable, and its design can be tweaked for all sorts of other crucial jobs.
And the adaptations are so cool. If you hook up the aneroid mechanism to a pen and a slowly spinning drum, you get a barograph. It gives you a continuous printout of pressure changes over time. Even more important, since we know air pressure drops as you go higher, you can adjust an aneroid barometer to measure your altitude. And that's exactly what an altimeter in an airplane is. It's just a barometer telling the pilot how high they are.
Okay, this is where it all comes together. We know what pressure is, we know how to measure it, so now for the big question. How does this help us figure out if we need to grab an umbrella on our way out the door?
Now this, right here, is the single most important thing to remember. Those old-timey barometers might have words like fair written next to a high number and rain next to a low one, but a real meteorologist cares way less about the exact number and way more about the trend. Is the pressure rising? Is it falling? Is it holding steady? That is the real secret to forecasting.
Let's break this down. It's actually pretty simple. Think of high pressure and low pressure as invisible hills and valleys in the atmosphere. Wind is just nature's way of balancing things out. It's the air flowing from the high-pressure hills down into the low-pressure valleys. So when you see the pressure rising, it means a high-pressure system, a hill, is moving in, usually bringing fair, clear weather. And on the flip side, falling pressure means a low-pressure system, a valley, is on its way, which often brings clouds and a good chance of rain. So I'll leave you with this thought. Right at this very moment, wherever you are, that vast ocean of air above you is changing. The pressure is either rising or falling. And now, by understanding what that little change means, you have the fundamental tool to make your own weather prediction. So, what's the pressure telling you?